We're starting off chapter 2 with finding instantaneous rates of change and slopes of tangent lines. Now, keep in mind the way that we have to do that in order to find an instantaneous rate of change is you're going to have to find an average rate of change over an extremely small interval. So you'll notice whenever it asks me to find the instantaneous rate of change or determine the slope of the tangent line in this section, I keep on taking an average rate of change of values right around the point that they're wanting me to estimate the instantaneous rate of change. Without calculus, we can't evaluate the instantaneous rate of change exactly. We can only use the algebra average rate of change formula in order to approximate it. But as long as we get very precise within our formula, we're going to get good answers. Okay, now let me go ahead and share my screen here with you and show you what we're going to be doing in this section. So whenever we look at this, I'll first take my work out and we can look at the first problem here. This is section 2.1, number 1. And you see it's just a physics application problem. This problem is having us look at the case when a ball is dropped from a state of rest at time t equals 0. The distance it's traveled after t seconds, and this is just the distance due to gravity, the position with respect to time is equal to 4.9 t squared meters. Now, it's asking us how far does the ball travel during the time interval between 4 and 4.5 seconds. Okay, so I know that in order to find out how far the ball has traveled, find the displacement between 4 and 4.5. All I need to do is say, well, it's the ending position minus the beginning position. Ending position is going to be the S of 4.5. Beginning position is going to be S of 4. Now, you see I already have the answer there. Where that came from is this right here. I said, okay, here's my formula. In order to find part A, the distance traveled between 4 and 4.5 seconds, I say the position at 4.5 minus the position at 4. And then I can say, well, all right, the position at 4.5, we're just plugging 4.5 into this equation. We get 4.9 times 4.5 squared minus 4.9 times 4 squared. And then we can say, well, okay, when we plug the 4.9 times 4.5 squared in, we get 99.225 minus the initial position of 78.4, we find that there's a displacement of 20.825 meters over this half of a second time period. Okay, so I go back and I put the distance traveled 20.825. Now it's asking me to find the average velocity over the time period between 4 and 4.5. Okay, so for that, all I did is I went in to my formula and I said, well, the average velocity is just distance divided by time. So I can say, well, I know the distance traveled was what I just found. The time elapsed is only a half of a second. So if you're traveling 20.825 meters in a half of a second, then you're traveling at an average rate of 41.65 meters per second over that half second time period. So that's what I entered in for my second answer there. Now the third answer involves quite a bit more work than the first part. It says by computing the average velocity over the time intervals. Now keep in mind what they were doing. We found the average velocity from 4 to 4.5. So over that half a second, it was approximately 41.65 meters per second. Now we're wanting to find out, well, what's happening at 4 seconds? Because I know that this ball, it's just going to speed up because gravity is certainly not going to slow it down. It's going to speed it up on the way down. So I know the average velocity from 4 to 4.5 is faster than the instantaneous velocity at 4. So in order to get a good grasp of what the instantaneous velocity is at 4, what they're having us do is evaluate the intervals between 4 and 1/10 of a second later, 4 and 1/100th of a second later, and 4 and 1,000th of a second later. So they're thinking, especially with this last one, that if you can find the average rate of change over 1/1000th of a second time differential, it's going to give you a really good idea of what the instantaneous velocity is at 4. Okay, let's see. Here's where I did this. Now, again, all these numbers came from me plugging these values into the calculator. I said the average rate of change between 4 and 4.1 seconds. Well, it's the position at 4.1 minus the position at 4 divided by the time differential, 4.1 minus 4, which is 1/10 of a second. S of 4.1, all I did is I plugged 4.9 times 4.1 squared into the calculator. And then, of course, S of 4, we already know, we did that up here, 78.4. When I figured this out, I got 39.69 meters per second. So I can say, okay, that's a much better idea of what the velocity is at 4 seconds than this, because this is over 1/2 of a second time differential. This is only 1/10 of a second time differential. So that a ball has not had time to speed up as much as it did in this case up here. But I can say, well, now the average velocity over this 1/10 of a second time period, 39.69 meters per second. Let's keep going. If you want to find the average rate of change between 4 and 4.01, only 1/100th of a second later, you say the ending position minus the beginning position, ending time minus beginning time. My ending position, all I did is I plugged 4.01 into this equation. 4.9 times 4.01 squared gave me 79.79249. When I subtracted the beginning position and divided by 0.01, I'm getting 39.249 meters per second. Now, what I would love for you to do is make sure you're noticing any changes as you're getting more and more exact, closer to the point of interest. Well, as I went from 1/10 of a second to 100th of a second, what happened to my answer? Well, my answer went down, it looks like 0.45, went from 0.69 to 0.24. So approximately 0.45, or you might even say closer to probably 0.44 since there's a 9 there, about 0.44 seconds. Now, I know it's never going to change that much again because each time interval change is getting less and less and less. I went from 1/10 of a second to 100th of a second time differential here. Now I'm going to go from 100th of a second to 1,000th of a second time differential. Ending position minus beginning position, ending time minus beginning time. When I plug 4.001 into this equation, I get the 78.4392049. I subtract the beginning position, divide it by my time differential, and again, please notice what I get. And you say, okay, where is the pattern? Oh, I'll tell you the pattern. Please notice from here to here, that first digit dropped 0.4. Please notice from here to here, that second digit is dropping 0.4. So hypothetically, if I said, I want to know what the average rate of change from 4 to 4.0001 is, I want you to immediately understand, oh, okay, this time it dropped a 4 in the first digit, this time it dropped a 4 in the second digit, next time that 4 will drop out of the third digit. It would be 39.20049. I'd say, gorgeous. Okay, so what's going to happen as that time interval gets closer and closer and closer and closer to exactly 4 seconds? Well, it's going to approach 39.2. So, and again, if you need to get more exact with these average rates of change in order to convince yourself of that, you always could. But you have to be careful. A lot of students don't want to take their decimals out to as many places as necessary. You don't want to get a wrong answer due to rounding error. So please don't think you can round to 3 decimal places within the problem and still see these patterns exist in your answer. It's not going to work. You need to be very, very precise as far out as the calculator will go with all these numbers within the problem. But now I can see, okay, there's an instantaneous velocity at 39.2, and you'll see that that is what I put for my instantaneous velocity for part C. Part C was quite a bit longer than the first 2 parts. but hopefully you'll agree it's quite a bit cooler. Now, question 2 kind of works off of that. When it's still the same physics formula, position with respect to time is equal to 4.9 t squared meters in t seconds. It's asking me to estimate the instantaneous velocity at 3 seconds. And it's wanting me to give my answer to 1 decimal place if necessary. Okay, so it's really not asking for a lot of accuracy here. So here's what I did. I said, well, if it's wanting to know what the instantaneous velocity is at 3 seconds, how about I find the velocity change, which, keep in mind, the average rate of change of position over time is velocity. So I'm calling it, or I'm abbreviating it over here, AROC, which simply means average rate of change from 3 to 3.01. But the average rate of change of position over time is velocity. So this first answer I found here is the average velocity from 3 to 3.01. I took the ending position minus the beginning position over end time minus beginning time. When I plugged 3.01 into this formula, I got this number, 44.39449. When I plugged 3 in, I had 4.9 times 9, which gave me 44.1. Subtract out the numerator, divided by 0.01, getting 29.449 meters per second. Now, I know that that answer may not be very accurate, so I go another decimal place and see if I can see a pattern. And I can say, well, the average rate of change from 3 to 3.001. So now I'm finding the average rate of change over 1/1000th of a second time differential. This should be a pretty accurate answer as to what the instantaneous rate of change at 3 is. When I try to do this, ending position minus beginning position divided by end time minus beginning time. When I plug that 3.001 into my equation up here, I got this 44.1294049. Again, please don't round that. I went every decimal my calculator gave me. I subtract the beginning position of 44.01, the position at 3, divide that by 0.001, got 29.4049. Now, when I'm thinking about this, the 29.4049, I'm saying, okay, what's the difference from here to here? You dropped 4 in the 100ths position. So this number is approximately 4/100ths less than this number. So if I were to ask you to guess what happens if I go and try to find the average rate of change from 3 to 3 1/10,000th, 3.0001, I want you to see that, well, you're just going to drop a 4 in the next position, and it's going to be 29.40049. Then the next one would be 29.4000049, then 29.4000049. You're like, well, what is that approaching? It's approaching 29.4. And you can see, even if you round this answer to 1 decimal place, you've already got it accurate to 1 decimal place. But I also want you to see that, yes, if you keep on making this interval smaller and smaller and smaller, your limiting value is going to approach this value right here. Instantaneous velocity at 3 seconds, 29.4 there. Now, for number 3, there's really nothing needed here. I went ahead and showed some work, but it gives me a linear function, and then it asks me what's the delta y over delta x. That's another word for slope. Remember, slope is the change in y over the change in x, which is also another word for instantaneous velocity. And I can say, well, the instantaneous velocity of this line, well, and actually it'd be an average rate of change since it's giving me the interval between 4 and 5. And I can say, well, the instantaneous, it's the same thing as the average velocity. The slope from any point to another point on a line is constant. Now, I went ahead and showed it out, and I said, well, delta y over delta x from 4 to 5 is going to be my function evaluated at 5 minus my function evaluated at 4 divided by 5 minus 4. Now, my function is 4x minus 4, so I plugged a 5 into the function here, Then I plugged a 4 into the function here. 4x minus 4 becomes 4 times 5 minus 4. That gives me a 16. Then I have that subtracted by 12, all divided by the one place between my two x values. So the change in y is 4, the change in x is 1. Did we have to do any of that work to know that? Of course not. You automatically know, well, John, it's just asking for the slope. The slope is just the coefficient of x, so you get your 4. And then it's saying, what is the slope of the tangent line at x equals 5? Well, the slope of the tangent line to any line is always the exact same slope as that line. So you just look back up and say, 4. That problem was not very good. Now, you're thinking, I hope number 4 improves upon that answer of 4 in the last problem. So am I. This one, it goes back to a physics vertical position function again. A stone is tossed vertically upward in the air from ground level with an initial velocity of 30 meters per second. Its height at time t is h is equal to 30t minus 4.9t squared. We're supposed to compute the stone's average velocity from 1/2 second to 2 seconds. No problem. I know that average rate of change from 0.5 to 2, it's going to give me the change in the height over the change in time. That's position over time. This is going to give me velocity. So the average velocity is going to be given from the average rate of change from 0.5 to 2. That's the ending position minus the beginning position over ending time minus beginning time. So we see we have a time differential of 1.5 seconds in this problem. In order to evaluate the ending position, you just plug 2 into your formula. You would have 30 times 2 minus 4.9 times 2 squared. And then you'd have plug 0.5 into your formula, 30 times 0.5 minus 4.9 times 0.5 squared. I went ahead and did all of that into my calculator. Of course, everybody's going to do that part in their calculator. My ending position is 40.4. My beginning position was 13.775. The change of position over the change in time gave me an answer of 17.75. Now, this would be in meters per second here. We didn't need to put the units just because I believe the units are already on achieve. Oh, they didn't on that one, but that's okay. In fact, they do not want units in there. So give to 2 decimal places, and it was already an exact answer to 2 decimal places anyway, 17.75 there. Gorgeous problem. Now, number 5's considerably longer, probably the longest problem in this section. It's still looking at that vertical position function with height. This time, my initial velocity was 32 meters per second. So my function h of t is 32t minus 4.9t squared. And then we're trying to estimate the stone's average velocity at a whole bunch of different values, and then with the end goal of finding the instantaneous velocity at 2. Let me go ahead and maximize this screen. So for number 5 here, the first one they were asking me for is to find the average rate of change, or the average velocity, from 2 to 2.01. Again, that's just ending position minus beginning position divided by end time minus beginning time. All you have to do for h of 2.01 is plug 2.01 into that equation. Make sure you don't make any rounding errors. We need the entire number, minus h of 2, you plug a 2 into that formula. My ending position minus beginning position divided by the time differential of only 1/100th of a second gives me an average rate of change here, or in this case, an average velocity of 12.351. And again, we don't need to put the meters per second just because it's already on the achieve system. So 12.351 is my average rate of change. Now, as I go, I would like to try to see if there's some pattern as I try to be more and more precise and approach 1. So this was the average rate of change from 2 to 100th of a second later. What about when I go from 2 to 1,000th of a second later? I do ending position minus beginning position, end time minus beginning time. h of 2.001 gave me the, and again, you're just plugging it into that equation, 2.001 gave me 44.4123951. We're subtracting the beginning position from that, dividing it by 1/1000th of a second, and I'm getting 12.3951. So as soon as I see that, I'm thinking, okay, what's the difference in this number and this number? Well, this number added a 9 into the second place, and it kept that 5-1. So now I already have the next one. I'm going to cover it up because I can't remember what the answer is. But if I were to guess what the answer to the next one, based upon what I've done right here, I would just say, well, okay, it should be 12.39951, I bet. And was it? Yes, gorgeousness, oh gorgeousness. Now, it's not the one, but it's 12.3995. So please notice, you should be able to recognize a pattern at some point. Then if I said, hey guys, what would it be from 2 to 2.4 zeros in a 1? You'd say, well, it's going to be 12.39939s and then a 5. And you'd say, okay, so as you get closer and closer and closer to 2, what is this value going to approach? It's going to approach 12.399999999999951. What number is that approaching? Well, it's approaching a number of 12.4. So I already know, the instantaneous rate of change at 2 is 12.4 before I even do the left-hand side. All of these would be considered the limit as x approaches 2 from the right. We're taking our second time that's always slightly greater than 2. But now if I want to see what happens as I'm trying to approach 2 seconds from below, so the first one has me find out what's the average rate of change from 1/10,000th of a second before 2 up to 2. So I still say ending position minus beginning position over end time minus beginning time. We already know h of 2 is 44.4. When you plug the 1.9999 into this equation, you get this number. We divide the beginning minus the ending position, we divide the end position minus the beginning position over the change in time. And in this case, I got 12.4005. Of course, that rounds to 12.4 whenever you're trying to round. Now, if I went in the other direction and say, well, what if I, instead of just 1/1000th of a second time differential, 1/10,000th of a second time differential, what if I do 1/1000th of a second differential? I'm thinking this should not be as good of an estimate, but it's still going to be really close. End time minus beginning time over ending position minus beginning position over end time minus beginning time. I'll get that right. Now, end time, ending position, that's our h of 2. We already know that's 44.4. When you plug the 1.999, that's where this interval began, we get a position of 44.3875951. You take the difference of that numerator divided by 0.001, and there needs to be a decimal in that denominator there. I forgot my decimal. Put that in there. We know that that's going to give me 12.4049. Now, I'm thinking that, okay, when I try to find the pattern from here to here, you can say, well, as you get more accurate, you're going to gain another 0 between the 4 and this number. Now, I bet that number is really 49. It just rounded it up to a 5 here. And so I can say, well, all right, so when I get more accurate, I'm going to have another 0, and it'll be 12.40049, which is what that is. What about my other answer? And I'll cover it up to not see it. But I bet it loses that 0, and I bet it's going to be 12.449. Let's see. Haha, gorgeous. Yep, gorgeous. So the least accurate estimation for those that's before 2 is when we just do a 1/100th of a second time differential. And you can see, I say least accurate, it's still pretty close. If you had to round any of these to 1 decimal place, you're going to get the answer of 12.4. So to 1 decimal place, you get it no matter which one you use. But please remember, the more accurate you are with your average rate of change, the less time that elapses here, the closer and closer and closer you're going to get. Now, in order to see the pattern, you need to do several of them out. I always usually do it above the value. I'm not really fond of doing it below the value, but they both work. There's going to be a pattern in either case. Now, when I'm looking at, let's see, whoops. That unknown. There. Couldn't minimize that screen for a second. Sorry, guys. So here we go. You can see I put all of those values in that I had, and you can see I have the instantaneous velocity at t equals 2. So now we can say, well, all right, that was not too bad of a problem. For number 6, these are all fairly similar. In number 6, we're looking at the position function t cubed plus 5t, and we're trying to find the average rate of change from 2 to 6. So I can say, well, the average rate of change from 2 to 6, that's just ending position minus beginning position over ending time minus beginning time. When I plugged a 6 into this function, it'd give me 216 plus 30, and I got the 246. When I plugged a 2 into the function, I would get 8 plus 10 for 18. We subtract the numerator, ending position minus beginning position, divided by the time differential of 4 seconds. And you can say, well, okay, then this is going at a rate of 57. And I don't think units was even given in this problem, so I can't call it 57 meters per second. It's just an average velocity of 57 units per unit, whatever it would be in this problem. And you can see that that is what they wanted. Now, the second question here is more challenging. And the reason it's more challenging is because it's asking us to find the instantaneous rate of change at 2. So instead of going throughout all of this stress and trying to find many different values, I just said, let's be very accurate, and then that should be a really good estimate of what the instantaneous rate of change is. That's what I did here. So you can see I said the instantaneous rate of change at 2 is approximately equal to the average rate of change from 2 to 1/10,000th of a second later. So I said, let's find the position at 2.0001 minus the position at 2 divided by my change in time, which is just 1/10,000th of a second. Now, your numerator is going to be your ending position minus your beginning position. Your ending position, I just had to plug a 2.0001 into this equation. This is what I got. I didn't want to make any rounding errors. I needed every single decimal there. When I subtract out my numerator and divide by 0.0001, I got 17.0006. So now, whenever it's saying, well, the instantaneous velocity or the instantaneous rate of change at 2 is, and I think it even told us to round to the nearest whole number, so that made this one really easy. Yeah, it said give your answer as whole numbers. So 17 was the only logical choice there. Now, speaking of the only logical choice, number 7 was an insultingly easy problem. And the reason I say that is because there's really no work to show on it. It gives you a function f of t is equal to 8t minus 7, and it's asking you to estimate the slope of the tangent line when t is equal to -9. And you say, well, you don't need to do work because the slope of the tangent line is going to take on the slope of the curve at any point. Well, the slope of this curve at any point is the constant slope of 8. So I just said it would be silly to show any work there. Our constant slope is 8, and we can eliminate that problem from consideration. For the next problem, which is number 8, it's a much cooler problem. It's asking me to find the slope of the line tangent to the curve, y equals the square root of 2t plus 1, when t is equal to 1. So you didn't have to graph out the function, but I did. The horizontal axis is my t-axis, and then of course the vertical axis is going to be my square root function. Sorry, my square root function. Wish this mouse would behave. There we go. So now I can say, when I'm looking at this, I'll get my function starts when t is equal to 1/2, and I know that the y value is 0, and then it's going to be your typical half parabola looking function there. We're trying to find out what the slope of the line tangent to the curve at 1 is. So I need to know how fast, what is the instantaneous rate of change of the slope of this curve when t is equal to 1. And then that's going to make the slope of this line tangent to the curve, and it's going to continue at that slope forever and ever and ever. Notice, since the square root function always continually starts to flatten off, flatten off, flatten off, this line is going to rise more quickly in that direction, and it's also going to be above the square root function in this direction too, because it really starts moving downwards after that. Now I can say, well, all right, in order to try to determine this, I'm going to find the average rate of change. If I want to know how fast is that function increasing at 1, how about I find the average rate of change from 1 to a point just 1,000th of a t value later, 1.0001. And if you're assuming t is time, well, this is a 1/10,000th of a second time differential. So I take my average rate of change formula. It's your function y evaluated at 1.0001 minus y evaluated at 1 over your change in t, which is just your 1/10,000th. When you plug the 1.0001 into this equation, you'll get 2.0002 plus 1. That's where this comes from, the square root of 3.00002. And then your second value, y of 1, is just going to be the square root of 3. So I used my calculator and I said, well, I need to find the square root of 3.0002 minus the square root of 3, all divided by 1/10,000th. And I got 0.577340647. Now, the Achieve system wanted this answer to 3 decimal places. So I said, well, easily, the slope of the line tangent to this curve when t is 1 should be 0.577. And you can see here, absolutely, that's what they wanted. For the next one, it's a very similar question. The problem I had was the exponential function 6e to the x, and it wanted to know the slope of the line tangent to this curve when x is equal to e. So what I did there, and again, you don't have to draw these out. I just wanted to show you what I was finding. I'm finding the line of the slope tangent to this curve when x is e. Well, when x is e, the y value is strange. It'd be 6e to the e. And so I can say, well, all right, my y value, it's pretty far up there. I know that this would have a y-intercept of 6. So I went ahead and drew out my function. But now the line that I'm trying to find the slope to is this right here. And it's going to tell us what the instantaneous rate of change of our curve is at that instant when x is equal to e. Okay, so since I don't have a nice derivative way to find the instantaneous rate of change at e, I use algebra. Algebra forces me to think of average rates of change. And I can say, well, an instantaneous rate of change, or the slope of the tangent line, is nothing more than the average rate of change over an increasingly small interval. So I make my interval from e to e plus 0.0001. I evaluate my function at e plus 0.0001 minus my function at e divided by 0.0001. And whenever I plugged this in, I literally just plugged in 6e, and then I typed in the exponent, e plus 0.0001, just like you see there. When I did that, I get this number right here, and put every single decimal my calculator would tell me. Minus 6e to the e gave me this number. We divide that by 1/10,000th, and when I did, I got an answer of 90.9301, you'll see there. Now, when I see that that answer is 90.9301, I know the achieve system is wanting the answer to 3 decimal places. I can say, well, then to 3 decimal places, I might as well just say it's 90.930. And if that's the case, it's better just to put 90.93. And that's what they wanted. Oh, actually, they just wanted 2 decimal places there anyway. The last one goes back to it's wanting 3 decimal places. It's wanting you to think of the function, the natural log of x, and it wants the equation of the line tangent to that curve when x is 1. Okay, no problem. I'll show that. Here's the work I did. I said, well, if f of x is equal to the natural log of x, and I want the line, or I want the slope of the line tangent to this curve when x is 3. Well, when x is 3, the y value is slightly greater than 1 up here at the natural log of 3. And you'd say, well, my function's going to have this slope. It's clearly going to be a positive slope, but it's not going to be a very large number. Let's find out what that number is. I can say, well, I know that the slope of that line should approximately be the average rate of change from 3 to a point just right after it. And again, I wouldn't ever get any less than 1/10,000th of a second. Once you start putting too many zeros, you're just going to run into round-off errors even on your calculator. So I think the slope would be very good approximated by the average rate of change from 3 to 3.0001, 1/10,000th of a x value later. I go in and I say, well, it's the ending position, my natural log function at 3.0001, minus the beginning position, which is my natural log at 3, divided by the change in the x values, which is my 0.0001. When I divided that out, I got 0.333277778. Now, because that logarithmic function is continually flattening, the average rate of change from 3 to 3.0001 is actually going to be a very, very slight underestimate for the slope. Please notice the slope is greater before 3 than it is after 3. It starts decreasing in slope. So because of that, if I were to ask you, is the actual slope at 3, is it greater than this or is it less than this? It's probably very slightly greater. In fact, if I had to guess, I guess it's 1/3. But to 3 decimal places, you don't have to guess. You know the answer is 0.333. Very cool problem. And you can see, absolutely, that was it. All right, guys, please do try the problems in this section and let me know if you have any trouble. I had fun doing it, and I hope you do too. But I'll be glad to help you if you get stumped on anything.